Hey everybody, this is the makeup video for the class that I missed teaching yesterday. I'm going to label this as Co-21A February 8th, 2024, even though I'm actually recording it on February 9th, just so that you can fill the attendance form with the correct day and not have any kind of confusion about that. My intention for this recording is to go over a couple of things that we haven't gotten to yet, namely reviewing the derivative rules, also talking about the derivative of trig functions once again, excuse me, as well as e to the x and also the chain rule. And then after I do those things, I'll talk about some problems that are similar to the practice midterm that McDonough posted. I know he's posted solutions as well. So I'll try and make up some problems that are very, very similar in nature to those, but not exactly the same. So let's go ahead and start with a review of the rules we know so far and the trig derivatives. So we have we'll just kind of make a whole list here. So power rule, the derivative of x to some power is that power times x to the previous power minus 1. So for example, the derivative of x to the 6th is 6 times x to the 5th. Or for example, if f of x is 1 over x to the 9th, which is the same as x to the negative 9th, then the derivative is negative 9x to the negative 9 minus 1, which is negative 10. I should grab some water while I'm thinking about it. Okay. There's also a couple rules that we kind of use very frequently that we don't often really talk about. I'll just point out, we have the addition subtraction rule. So meaning if you add or subtract functions together, you can add or subtract the derivatives. Very generally, we can write it as the derivative of f of x plus g of x is just equal to the derivative of f of x plus the derivative of g of x. And then since it doesn't matter if we subtract either, it's f plus g is f prime plus g prime, or the derivative of f minus g is f prime minus g prime. So another example of this would be like, say, for example, so I'm trying to fit things on the side here. For example, here, the derivative of, say, x cubed plus x to the 5th would equal the derivative of x cubed plus the derivative of x to the 5th. We use it all the time. We just never really think about doing it. There's also the constant multiple rule. Again, these two rules are the ones I think of using all the time without actually explicitly stating that we're using them. The derivative of a constant times a function is the constant times the derivative of the function. An example of this might be something like the derivative of, I don't know, 8x to the 5th. Really, what we often do is just say, oh, it's 8 times 5, which is 40 times x to the 4th. But the step that we're taking there was we're really actually thinking of this as 8 times the derivative of x to the 5th, which is 8 times 5x to the 4th, which is 40x to the 4th. Same deal. Along with this, the derivative of a constant is always going to be 0. So that's not really a rule, but we might as well say it anyway. Doesn't matter how funky the constant looks. The derivative of 5 is 0. The derivative of 8 is 0. The derivative of 8 was not 0 here because it was multiplied by a function. But if you have just a constant on its own, its derivative is 0. The derivative of e to the 33rd power, I don't see any variables there. The derivative is 0. Okay, but now for the rules that we kind of use a little bit more explicitly, we have the product rule, which is that the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. I always think of it as the derivative of the first function times the not derivative of the second function plus the not derivative of the first function times the derivative of the second function. Derivative and the not derivative in every way you can get it. We have the quotient, and we'll do some examples of these after I write them all down. We have the quotient rule, which is that the derivative of f of x divided by g of x. And I will say, I actually write this slightly differently than I say it. So I say it as the bottom times the derivative of the top. But I write it as the derivative of the top times the bottom. It's still the same thing. Bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. And lastly, what we haven't talked about yet, which I will get into in a minute here, is the chain rule. So very kind of formulaically, the chain rule says that the derivative of a composition of functions of f of g of x is equal to f prime of g of x times g prime of x. The way I would usually say it is, if I'm taking the derivative of a function of some stuff, where the stuff is like g of x, it's going to be equal to the derivative of the outer function, leave the inner stuff alone, multiply by the derivative of the inside stuff. That's how I like to say it and think of it. And then before we get to doing a bunch of examples here, I'll remind everybody about our trig derivatives. You should memorize your trig derivatives. They're going to keep coming up over and over. A reminder that all the co-functions, cosine, cotangent, cosecant, have negative derivatives. And there's not a good word for the not co-functions. All the other ones, sine, secant, and tangent, have positive derivatives. Here they are. So trig derivatives over here. The derivative of sine of x is equal to cosine of x. I do recommend writing them in this pattern where it's sine, cosine, and tangent, because sine divided by cosine is tangent. The derivative of cosine of x is equal to negative sine of x. The derivative of tangent of x is equal to secant squared of x. And then the reciprocal. So the reciprocal of sine is cosecant. The derivative of cosecant of x. I don't know why that parentheses there, not here. I said parentheses over there. Derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of secant of x is secant of x times tangent of x. And lastly, the derivative of cotangent of x is negative cosecant squared of x. And I'll point out there's a nice pattern here that I mentioned before. The derivative of tangent is secant squared, and you slap on a co in front of each of those words. So tangent becomes cotangent, secant becomes cosecant. The derivative of cotangent is cosecant squared, negative. Similarly, the derivative of secant is secant times tangent. You put a co in front of every function. The derivative of cosecant is cosecant times cotangent, negative. Kind of cool. All right, so we have all these rules, and then we can kind of do many things with them. For example, let me choose some examples here of all of them. So for example, if I want to find the derivative, actually, before I get to examples, there's one other thing I want to say, sorry. I did want to kind of talk a little bit more about why the chain rule have to do this. So here's my example of kind of a nice how the chain works. And there's actually, yeah, there's actually two kind of nice examples here. So one example, let's look at the derivative of, say, sure, 5x cubed plus 1 squared. Normally, you can think of the derivative of x squared as being 2x. I've got some stuff squared. It might seem like the derivative would be 2 times your stuff. But we're going to be missing something. Let's actually multiply that and see. So another way we could go here, as long as that power is not too terrible, is actually multiply this out and then just take the derivative. So the derivative of 5x cubed plus 1 squared, well, if I square this, it's going to be the first thing squared, so it's going to be 25x to the 6th plus 5x cubed times 1 plus another 5x cubed times 1, so it's going to be 10x cubed plus 1 times 1 is 1. Take the derivative of that, you're going to get 25 times 6, which is 150 x to the 5th, plus 3 times 10, 30x squared. And now I'm going to factor out I'm gonna do this kind of in a weird way. So I'm gonna factor out the biggest thing I can, which is gonna be a 30. A 30, yeah. A 30x squared. Here I'm left with a 5x to the third plus 1. I'm gonna rewrite this as 2. So I'm gonna break up the 30 times x squared as a 2 times a 15x squared. I'm gonna leave the 2 in front and write the 15x squared at the end. But look, 15x squared is exactly the derivative of that stuff right there. You can see, at least from this example, that it seems like the chain rule totally works. And it does. If you had something to a higher power, which you couldn't multiply, like for example, the derivative of, I don't know, 6x to the fourth plus 7x plus 1 to the 101st power, it's technically possible to multiply by that, and never should ever do it. The derivative there would be, well, I've got some stuff to the 101st power. My derivative was 101 times that same stuff to the 100th power. 100th power? Yeah. 101 minus 1. And I have to multiply by the derivative of that inside stuff. So it's going to be a 24x cubed plus 7. And if I write it like that, it's kind of wrong because this says 101 times all this to the 100th power times 24x cubed. And then after you've done the multiplication, add on 7. Really, that's wrong. It should be this times this to the 100th times all of this in parentheses. The derivative of your stuff, if there's more than one term, has to be in parentheses. So all of this is say here. Sure, we can do one more. Let's say I have the derivative of something like, I don't know. Sure. Let's say we have something like x cubed plus 7 to the 8th power times cosine of x. So here, I actually kind of see this as being a product rule first. I have a product of two functions, this function and that function. X cubed plus 7 to the 8th and cosine x. So it's going to equal, this is where you might want to write this first. I'm going to call this f, this is g. And I'm just going to write down f prime. So x cubed plus 7 to the 8th prime times cosine of x left alone, plus switch it up. Leave the first part alone, multiply by the derivative of the second part. Which you can view if you wanted to. You don't need to write this, but you can think of, oh yeah, my f prime times my g, that's my f, and g prime. Following the rule for the product. And then we actually have to take this derivative still. So now I have to use the chain rule. The derivative of something to the 8th power is 8 times my something, the 1 less power, times the derivative of the inside, which is 3x squared plus 0, or just 3x squared, times cosine of x. And I'm going to be a little bit smart here. And I'm going to have this times the derivative of cosine. The derivative of cosine is negative sign. So instead of writing plus this times negative sign, I'm going to write minus x cubed plus 7 to the 8th power times sine of x. And that's my answer. So what I've been showing you is actually what's called the kind of power, the chain rule version of the power rule, where instead of saying the derivative of x to some power is equal to that power times x to the power minus 1. Now we're saying the chain rule version of it, which is the derivative of some function to the power is equal to that power times the function to the power minus 1. But then we have to multiply by the derivative of the inside. Technically, we're doing that here as well. It's just the inside is x and the derivative of x is just 1. So you can slap on the times 1 out here if you don't need to. Sure. We could prove this rule. It's actually not that hard to prove. You could also skip it. So I'm going to prove it real quickly just so you can see it. I don't think it really is that valuable though. So if you want to skip it, please feel free to jump ahead. So let's point it. So I'm going to use what's called the repeated product rule. So as a reminder to everybody, maybe not a reminder, but to show everybody, it's true that the derivative of f times g is f prime g plus f g prime. But this product idea can actually be extended to a product of any number of things. So I did the product of f times g times h, derivative of that. I can think of it as, say, like f times g is the first thing, h is the second thing. So product rule says it's the derivative of the first thing times the second thing plus the first thing left alone times the derivative of the second thing. But then using the product rule from up here, the derivative of f times g is f prime g plus f g prime all times h plus f times g times h prime. We're multiplying it out by distributing the h here. It's going to be f prime times g times h plus f times g prime times h plus f times g times h prime. Well, as I like to view it, if I'm taking the derivative of three things multiplied together, I get three things added together, and each of those things, you always get one derivative and the rest not derivatives. And each derivative, f prime, g prime, and h prime, has to show up exactly once. So I could say that the derivative of a product of four things, f times g times h times j, I know what the answer is going to be. It's going to be four things added together, and each thing is going to have one derivative and three not derivatives, and each derivative is going to show up once. So f prime once, and g prime once, g prime once. Or you could still use the rule. You could say, hey, look, I'm going to think of this as the product of two things, f and g and h and j. So that's going to be the derivative of the first thing, the derivative of f times g, times the other thing left alone, h times j, plus f times g times the derivative of the second part, which is the derivative of h times j. And then using the product rule, that's going to be, well, the derivative of this is going to be f prime times g plus f times g prime times hj, plus here I'm going to have fg times h prime j, with the j, plus hj prime. If you just rip the whole thing out, oh yeah, look, we get exactly f prime times g times h times j, plus f times g prime times h times j, plus f times g times h prime times j, plus f times g times h times j prime. Just like I said, four things added together. Each thing has one derivative and three not derivatives, and each of the derivatives shows up exactly once. F prime, g prime, h prime, and j prime. And you can keep going. You can do 5 things, 6 things, 7 things, and the pattern will. Why this helps us see this is then I can say that the derivative of f of x to the pth power, assuming p is a positive integer, which it doesn't always have to be for this to be true. We're going to assume it to be true to show it once here. You're going to get the derivative of, I'm going to write f instead of f of x. This is a little less cumbersome. F times f times f times f p times. So instead of having the product of 4 things, I have the product of p things. And just like when I had the product of 4 things, and I got 4 things added together, each derivative showing up once, all the rest not derivative, I'm going to have the same idea here. So now I'm going to have p things added together. Each derivative is going to show up once. So the first one is going to have f prime times f times f times f all the way to f. Plus the next one's going to have f times f prime times f times f times f. And you can probably see where this is going. F times f times f prime times f all the way to f. All the way until the very last one has all f's first. And the very last one's f prime. But this is really just f prime times f multiplied together p minus 1 times, right? Because there's p of them here. One of them is derivative, the rest are not. This is really f prime times f to the power of p minus 1. So is this f prime times f to the p minus 1. And so are all of them. And how many of them are there? Oh, there's p of them. So really you have something added to itself p times. And just like 5 plus 5 plus 5 plus 5 plus 5 plus 5, 6 times, really just 5 times 6. This plus this plus this plus this, p times really just p times all of that. And then I would much rather write it as p times f of x instead of just f, the p minus 1 times x. And that's my chain rule version of the power law. Now, the nice thing, the wonderful thing about the chain rule is that it works for any kind of function, not just something to a power. Let me show you one more example of how the chain rule kind of works, and then we'll just do more examples. So we've seen a couple times the derivative of sine of x is equal to cosine of x. There's a lot of nice ways to show this. You can use a little definition. You can also show it graphically, which I think I did once or twice in class. I'm gonna do it again because I want you to see it then. So let's graph one period of sine. It starts at the origin, and then at pi over 2, it goes up to 1. And then at pi, it goes back to 0. And then at 3 pi over 2 goes down to -1. And then 2 pi back to 0. And then we talked about graphing its derivative. And we say this is, y equals the sine of x. And graph its derivative by looking at the slope of the tangent lines. So right here, slope of the tangent line is 1. And right here, the slope of the tangent line is 0. And right here, the slope of the tangent line is -1. Right here, the slope of the tangent line is 0. And right here, the slope of the tangent line is 1 again. So if we graph this, it looks, not surprisingly, like the graph of cosine of x. Good. Now what we're going to do is we're going to try graphing. We're going to look at how we do graph sine of 2x. I graph y equal to sine of 2x. I want to point out that all this does to the sine graph is it shortens the period. Instead of the period being 2 pi, the period here is now 2 pi divided by 2, which is pi. So we have the same kind of sequence here, except from 0 to pi. So instead of doing middle, top, middle, bottom, middle, all that's going to happen from 0 to pi. So my quarter of a period is now going to be 1/4 pi. And the middle, top, middle, bottom, middle. And the graph looks like this. And maybe you can say, well, let me zoom in for a bit so you can see it really well. So there you go. There's in blue. You can kind of see the color difference there. There's my sine of 2x. And let's go ahead, let's go ahead and draw the second period as well. It's the same thing. And go again, top, middle, bottom. I'm sorry. Top, middle, bottom. Cool. Now let's try graphing the derivative by looking at the slope of the tangent lines. So we're going to get these points here. So at pi over 4, which is halfway between 0 and pi over 2, the slope is 0. And at 3 pi over 4, same deal, slope is 0. And at the origin, the slope, well, look, that graph is steeper than this graph. It actually has a slope of 2, not 1. Similarly, right here, the slope there is steeper than -1. It's actually -2. Sorry, I'm screwing the graph here. That point came from. I don't know where that point came from. Sorry. And then finally, back at pi, the steepness is again +2. So this point, this point, this point, this point. So I don't know where that came from. Sorry. And it looks like this. It looks like the cosine graph, except it's been smushed in. So I definitely have a cosine of 2x because the period is pi instead of 2 pi. But I also have stretched the graph by a factor of 2 vertically. The amplitude is 2. So I'm going to multiply by 2. Or in other words, the derivative of sine of some stuff is cosine of the stuff times the derivative of 2x is 2. So here we can see at least one example of a not powerful version of the chain rule totally working the way one would expect it to work. Kind of great. And then just kind of one more thing in reference to practice exam. I do see that he also has some e to the x on there. So I will point out that the derivative of e to the x is e to the x. There are lots of ways of talking about this. If you do it with a limit definition, you could say that the derivative of e to the x is equal to the limit as h approaches 0 of e to the x plus h minus e to the x over h, which is the limit as h approaches 0 factor out of e to the x. And then you have to do something kind of tricky. You have to know that, yeah, I mean, this is kind of, I feel like this is a little hand wavy, but I want to have some sort of justification for why we just say this is a thing like that. It's just, I'll point out that it is true that the limit as h goes to 0 of 1 plus h to the 1 over h is equal to 2. Kind of a funky limit. We can talk more about it later, but I will yeah, you can graph it. In fact, let's go ahead and graph it on best notes just so you all can see. Might as well do that. Sorry, 1 second. Do this real quick here. Share on the screen appropriately. Share here. So, for a second. So I'll just point out, right? If you look at, I'm going to do 1 plus x to the 1 over x. There's 1 plus x to the 1 over x. It's very not well defined for a lot of it. But you can see here that as if I look at the table, so for values of x to get closer and closer to 0, so I'm going to plug in like 1, like 5, like 1, like 0, 1, like 0, 0, 1, 1, 0, 0, 1, like 0, 0, 0, like you're getting very, very close to a number that we recognize as being. Oh, that's weird that it got further. That seems like an anomaly there. Sometimes calculators do weird things, but that's the idea. Is that, oh yeah, this expression 1 plus x to the 1 over x and x is closer and closer to 0. The values get closer and closer and closer and closer and closer. So here's how that we then use that trickiness to help us get the thing we're looking for. So what we're going to do is we say, okay, well look, this limit 1 plus h to the 1 over h is e, and vice versa. E is equal to the limit of h equals 0 of 1 plus h to the 1 over h. So what we can do is we can replace this e with that because the limit is already there. Right? If you replace e with 1 plus h to the 1 over h, you're still taking the limit of that. So that's where it's a little kind of hand wavy, I would fully admit. And then we're going to say this is equal to the limit as h goes to 0 of e to the x times e to the h is going to get replaced by, sorry, e is going to get replaced by 1 plus h to the 1 over h. But then it's e to the h, so that's going to be raised to the h power minus 1. And now hopefully you can see what's going to happen. The 1 over h to the h, those are going to multiply to 1. So you're going to have the limit as h goes to 0 of e to the x times 1 plus h to the 1 minus 1. But then 1 minus 1 cancels. H divided by h is 1. And you have the limit as h goes to 0 of e to the x, which is just e to the x. So the derivative of e to the x is e to the x. Cool. I do not love how giant this is on my screen. I'm going to make it less giant. And then, sorry, I keep thinking of like other rules, I should say. So then one more thing I would say is that every derivative has kind of a chain rule version of it. So just like if there's some stuff to a power is this power times the stuff to the power minus one times the derivative inside stuff. The same as trig functions, right? I'm not gonna write them all down, but it's like the derivative sine of x is equal to cosine of x. And the chain rule version, the derivative of sine of some stuff is equal to cosine of the stuff times the derivative of stuff. Or let me give you two more. I'll do the non-co functions. The derivative of tangent of x is secant squared of x. And the derivative of tangent of some stuff, or you can say tangent of f of x if that is nice for you. The tangent of f of x, some stuff, is secant squared of your stuff. And the derivative of your stuff. Or if it's also kind of weird when it's secant. The derivative of secant of x is secant of x times tangent of x. And the derivative of secant of some stuff is secant of your stuff times tangent of your stuff times the derivative of your stuff. Also true for the other three functions, cosine, cotangent, cosecant. And then also, we just said the derivative of e to the x is equal to e to the x. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So for example, I can say something like the derivative of cotangent of x cubed plus e to the x. Well, the derivative cotangent of x is negative cosecant squared of x. So the derivative cotangent of some stuff is negative cosecant squared of that stuff times the derivative of that stuff, which you could either write as the derivative of that stuff, or you can skip this step and just say it's negative cosecant squared of x cubed plus e to the x times the derivative of my stuff is 3x squared plus the derivative of e to the x is e to the x. And that's my answer. Or I could ask something like, what's the derivative of e to the x to the fifth plus x? And then it's going to be e to the stuff times the derivative of the stuff. End of story. Make it more complicated. I could say, what's the derivative of e to the x cubed times cosine of x squared, which seems super annoying because it's a product rule, and then each part of the product has a chain rule. So it's going to be the derivative of e to the x cubed times the not derivative of cosine of x squared plus e to the x cubed times the derivative of cosine of x squared. You could skip this step and then say the derivative of the x cubed is e to the x cubed times the derivative of x cubed times cosine of x squared plus the e to the x cubed alone. The derivative of cosine of x squared is, I wasn't smart, I didn't look ahead, is negative sine of x squared times the derivative of x squared, which is 2x. Lots of things. So let's go ahead. I'm going to go ahead now and look kind of through this practice again that McDonald posted and see if there's anything of note. Oh, some quotient rule. So I'll just try and throw some problems into those similar things. So he says f of x equals, I'll say like it's x to the sixth minus 3 cosine of x plus x plus 5. The derivative, we're just taking the derivative of each part. It's going to be 6x to the fifth. Derivative of cosine of x is negative sine x, so it's negative 3 times negative sine of x, which we could have written as positive 3 sine of x. Derivative of x is 1, derivative of 5 is 0. You don't need to write plus 0, but it doesn't hurt to write it. I wouldn't simplify, right? He's in the instructions here, it says compute the derivative. These should be given as functions of x, and you compute it using whatever method you prefer. You should not use the limit definition of the derivative that is explicitly asked to. You might have something like this. G of x equal to 7x squared plus tangent of x over e to the x minus 5x. And I'm going to take the derivative. I'm going to use the quotient rule. So it's going to be the denominator or the bottom times the derivative of the top, which is, you can write this out as 7x squared plus tangent of x prime, but if you're trying to save yourself time and space, I would probably just take the derivative if you didn't feel too complicated. Derivative of 7x squared is 14x. The tangent is secant squared of x. Minus the top times the derivative of the bottom. The derivative of e to the x is e to the x. The derivative of 5 is 5. Sorry, the derivative of 5x is 5. All divided by the denominator squared. No one asked me to simplify this. I'm not going to simplify it. Especially this. Like this, you could simplify and write it as 6x to the 5th plus 3 sine of x plus 1. But there's this thing here, there's no value. Okay, I like this next question because it looks super duper tricky. I feel like this next question actually is almost too tricky because if I said, my function was, I don't know, if I said my function was like e to the 81 plus 5 squared, you might be more likely to be tricked because, oh, the derivative of e to the stuff is e to the stuff. But it's not. Because, well, it is. So I'll say you could use the chain rule and say the derivative of e to the stuff is e to the stuff times the derivative of the stuff. But the derivative of 81 plus 5 squared, 81 plus 5 squared is 81 plus 25, which is 106, and the derivative of the constant 106 is 0. That's really e to the 81 plus 5 squared times 0, which is 0. But in reality, what we really should have done is said, oh, e to a thing that doesn't have any x's in it is a constant, and the derivative of a constant is always 0. On the other hand, this next problem, he gives you tangent of x times e to the x squared. I'm going to give you something totally different. Let's say our function is e of x equal to secant of x times e to the x to the 4th. Once again, the product rule rears its ugly head. The derivative is going to be the derivative of secant, which is secant of x times tangent of x, times leave the other thing alone, plus now you flip it. Leave the first thing alone, multiply by the derivative of the second thing, which is going to be e to the stuff, times the derivative of the stuff. And that's it for that one. Let's see what else we got here. I like this question. Yeah, it's kind of a tricky question. So he gives some terrible looking function. I'm going to make up something slightly different. Let's say our function here, and I'm just going to give you the factor version. Yeah, we'll do this. Let's say it's, yeah, sure. X minus 2 times x plus 4 times x minus 1 squared over x minus 2 cubed times x plus 1. And the first question is, find the limit. X approaches, sure, let's say 5 from the right of g of x. And the first thing you should do is just plug it in. You do the limit, x approaches 5 from the right of g of x and of x minus 2 x plus 4 x minus 1 squared. It's probably going to turn out to be not very nice, so let's move this up. Plug in 5, I'm going to get 5 minus 2 times 5 plus 4 times 5 minus 1 squared over 5 minus 2 cubed times 5 plus 1. That's going to be some number. If I was running short on time, I might not simplify this. I probably would have started off by writing this as 3 times 9 times 4 squared over 3 cubed times 6. And I happen to get lucky here. 3 times 9 is 27. 3 cubed is 27. Those divide. And I'm left with just 16 over 6, which is just 8 over 3. And that's it. If you plug in what x is approaching, 5 in this case, you can get a real number answer. That's your Okay, but now let's look at the limit as x approaches 2 from the left. I'm just going to put it in there. This problem I feel like is maybe extra tricky. If you just plug in 2 from the get-go, you're going to get the 0. 2 minus 2 is 0, and it doesn't matter what the rest is on top, because 0 times anything is 0. 2 minus 2 is 0. 0 times anything is 0. So it was 0 over 0, but here's the thing. 0 over 0 often means do more algebra. It doesn't really here, or what it really kind of implies is we should have, before taking into this limit, or really actually this limit, we should have canceled any factors that cancel. So what I should really do is I should rewrite this as the limit as x approaches 2 from the left of x minus 2 over x minus 2 cancels, leaving 1. None on top, 2 on the bottom side. X plus 4 and x minus 1 squared over x minus 2 squared times x plus 1. So that now when I plug into, I don't get 0 over 0. I get not 0 on top. I do get a 0 on the bottom. And when you have a not 0 over 0, we know the limit is going to be some sort of infinity. Or it could be does not exist if it was a two-sided limit, not a two-sided limit. So I'm going to plug in 2. We get 6 times 2 minus 1 is 1 squared over 2 minus 2. But so now the 2 minus 2 is where we have to be careful. 2 from the left is slightly smaller than 2. So it's going to be a slightly negative number, but it's being squared. And then 2 plus 1 is 3. Positive, 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 and the negative number squared is still positive. So the whole thing is positive, it means positive infinity. What that means is we do have a vertical asymptote at x equals 2. Because the limit as x approaches 2 from the left, or the limit as x approaches 2 from the right is some sort of infinity. It actually doesn't have to be true on both sides, it has to be true on at least one of the sides. It would also be true that the limit as x approaches 2 from the right of g of x would also be positive infinity for the same reason. You get 6, 1 squared. That is a 1, by the way, not a negative 1. That kind of said that. And then you have a slightly positive number, so it's slightly positive, and 2 plus 1 is positive 3. So it'll still be positive, 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 and you'll still get positive. So this graph, if you were graphing this right at 2, your vertical asymptote would look like it was going up on both sides. Not that we're being asked to graph it, but just so you are aware. The next part of this question asks to find all vertical asymptotes. 2 was definitely the KG one. Like if you look at the original expression, plugging in 2 means you get 0 over 0. It's not immediately obvious that you're going to get the vertical asymptote there. On the other hand, x equal to negative 1 is obviously a vertical asymptote because x equal to negative 1 makes the denominator 0 and the top is not 0. So the other vertical asymptote is going to be at x equal to negative. It should be x equal to whatever the value is. Okay, vertical asymptote isn't just negative 1, it's x equal to negative 1, or x equal to positive 2. So your horizontal asymptote isn't just whatever the number is, it's going to be y. For the horizontal asymptote, I guess this is part C here. For the horizontal asymptote, you have to compare the power on top of the power on the bottom. So here, if you were to actually let's look at the simplified version. So we look at the limit as x goes to infinity of the simplified version here. X plus 4 x minus 1 squared. X minus 2 squared times x plus 1. If you were to multiply this out, I'm not really going to multiply that. Watch what I'm going to do here. I'm going to have x plus 4 times x squared plus whatever. And then here I have x minus 2 squared, which is x squared minus whatever. I only really care about the times. X plus 1. If I multiply out the top is going to be x squared times x is x cubed plus lesser powers of x. The bottom is also x cubed plus lesser powers of x. And since the degrees are the same, The limit is the quotient of the leading coefficients, which is going to be 1/1. So my horizontal asymptote is y equal to 1. In the example he gave there, so in the example that's on his actual practice exam, which looks like this, the degree on top is 3, the degree on the bottom is 4, which means the horizontal asymptote is going to be 5. Because the bottom is faster. Okay. Okay, we have a limit definition question. I'm going to pause this. Yeah. Not the screen, so I'm going to pause the video. Okay, back to this similar question to this practice test. We have a limit definition. Let's make a new one. Let's say we want to find. So compute. Yeah, H seems like a terrible choice. H prime of t. I don't love it. H prime of t using the limit definition for, let's say, h of t equal to, I don't love that function. I'm gonna make up one. Let's say it's 2t squared minus 1t. So first things first, we the limit, and this is where I don't love the choice of h as a function in here, because usually we do the limit as h approaches 0 of h of the variable plus h minus h of t all over h. T not perfect. I guess we could use delta t if you prefer. The limit as delta t approaches 0 with h of t plus delta t minus h of t over t. Probably, sorry, probably a better choice. I don't know what he's going to do in class. But using, if you're using h typically as a thing like it's a small thing, it's over 0, calling attention to h. So we'll do it this way. This is going to equal the limit delta t goes to 0. H of t is 2t squared minus 5t, so h of some other stuff is going to be 2 times that other stuff squared minus 5 times that other stuff, and minus h of t. The h of t is just going to be the 2t squared minus 5t over delta t. The stuff that's going in here is the t plus delta t. Now, so then we simplify with the goal of canceling out this original delta t and delta. And man, what's this problem? Okay, so maybe it's the delta t. Anyway, our intermediate goal is to be that everything in the numerator that does not have a delta t should cancel out. You have 2 times t plus delta t squared is going to be t squared plus 2t delta t plus delta t squared minus this root of 5t minus 5 delta t minus 2t squared plus 5t. Cancel the 5t. You can use whatever thing you like, right? You can use h or delta t or some other thing. Typically, delta the variable is common choice if you want. Should be this 2. The limit is delta t goes to 0. 2t squared plus 4t delta t plus 2 delta t squared minus 5 delta t minus 2t squared all over delta t. 2t squared and negative 2t squared cancel. Everything has a delta t in it, so I'm going to factor out a delta t from the top, still writing the limit. Here I'm left with a 4 times t. Here I'm left with a 2 times delta t. Here I'm left with a minus 5. That divides to 1. We have the limit of delta t goes to 0. 4t plus 2 delta t minus 5 This part's gonna go to 0, equals 4t plus 0 minus 5, or 4t minus 5, which is exactly what we expected the derivative of qt squared minus 5t to be. Okay. I kind of like this fill in the blanks question here. I think it's a good way of getting you to think about how we should be doing this delta of something thing. So I'm just going to do this one as is, just to kind of show you an example of it. Fill in the blanks of the statement of what needs to be proven to show that the limit as t approaches 2 of h of t equals 12. Don't show your work, don't prove it. So for every epsilon that is greater than 0, there exists a corresponding delta that's also greater than 0, right? Because the epsilon delta is relatively positive. Such that, so usually I write this a little bit different. I usually write this as such that if absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Where in this particular case, my a would actually be 2, my limit would actually be 12, and I should actually be using, instead of x, I should be using t. Instead of f of x, I should be using h of t. But then he's actually writing this part first. So if this, then this is the same as this is true whenever this occurs. I know it's kind of backwards, but oh well. So we need that our function minus our limit is less than epsilon. So the absolute value of h of t minus 12 is less than epsilon. Whenever absolute value of x minus a, or the absolute value of t minus 2 is less than delta. Now there's space for something over here as well. And that's because technically the difference between t and 2 should be delta, but it should always be positive. Because remember, when we're taking a limit as t approaches 2, t is getting really, really close to 2, but not actually equal to 2. So the absolute value of t minus 2 being strictly greater than 0 means that t can get really, really close to 2, like 2.0000001, 1.99999, but t can't ever actually equal 2, because if it did, 2 minus 2 would be 0, and then 0 wouldn't be bigger than 0. So we need that 0 over there as well. That's all there really is to say about this problem. You just need to make sure that you have if the absolute value of your variable minus what you're approaching is less than delta, and this is just to say bigger than 0, then the absolute value of your function minus your limit should be less than epsilon. Average rate of change. So I'm going to change up the function again, but I'm going to do the same kind of problem. So let's say that we have x of t equal to, try better, 12t minus cosine of t plus the sine of t. So then if I want to find the average rate of change from t equals 0 to t equals, let's go pi over 6 here. Then it's going to be x of pi over 6 minus x of 0 over pi over 6 minus 0. X of pi over 6 is going to be 12 times pi over 6 minus cosine of pi over 6 is 4 sine of pi over 6 minus x of 0. And yeah, x of 0 is going to be 12 times 0 minus cosine of 0 minus 4 sine of 0 all over pi over 6. So he said for full credit, you shouldn't have any trig functions in your answer. So I would do one more thing. So 12 times pi over 6 is 2 pi. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. 4 times 1/2 is 2. Minus 0 minus cosine of 0 is 1. Minus 1. I mean, sine of 0 is 1. And this problem does not say that we should simplify our answers. Just that for full credit, you should have a trig function in your final answer. So I would leave this like this. Yeah, you could simplify this. You could make it 2 pi minus root 3 over 2. 2 plus 1 is 3. And then instead of dividing by pi over 6, you could multiply that by 6 over pi, and you can even distribute if you wanted to. So this times this, the pi is canceled, you get 12. This times this, you can cancel the 2, you get 3 over pi, and that would be 18 over pi. But I really, really, really don't think you should do that. You should leave your answer like this. Okay. How about the instantaneous rate of change at t equal to, I'm going to pick pi over 6 again, personally. So then instantaneous rate of change, we're taking the derivative. So that's going to be x prime of t. We're going to plug in pi over 6. So that's going to be 12. Derivative cosine is negative sine. So derivative negative cosine is positive sine. And the derivative sine is cosine. So 4 cosine of t. Then plug in pi over 6. X prime of pi over 6 is 12 plus the sine of pi over 6, which is 1/2, plus 4 times cosine of pi over 6, which is 4 times. It's going to be 12 plus 1/2 plus 4 times root 3 over 2. And again, don't simplify this unless specifically asked to. Acceleration, take the second derivative. So the acceleration, which I can spell, is going to be x double prime of t. Second derivative here is going to be 0. Derivative sine of t is cosine of t. Derivative 4 cosine of t is negative 4 sine of t. Then plug in pi over 6. 0 plus cosine pi over 6. This feels just like more of a problem of like, can you find trig functions of values? That's going to be cosine pi over 6 minus 4 times sine of pi over 6. Which is going to be root 3 over 2 minus 2. Sorry, root 3 over 2 minus 2. I wouldn't worry about the fact that this is negative. It's not a big deal. And we apologize for just playing this. Finally, just to answer his bonus questions, because I do think I kind of like them. Bonus question: when we take the derivative, we call this deriving, differentiating, or either one's fine. Either one is not fine. When you derive something, you derive an equation. For example, we derive that the trig identity sine squared x plus cosine squared x equals 1. Right? For example, if you use the unit circle, this length is 1, this length equals theta. This side here, I'm going to call it y. This side here, I'm going to call it x. Cosine theta equals x over 1. Sine theta equals y over 1. And then x squared plus y squared equals 1 squared, or x, which is cosine squared theta, plus y, which is sine squared theta equals 1. We just derived that formula. We were deriving a formula. We weren't taking a derivative, we were deriving a formula. On the other hand, differentiating is the correct thing to say when we're taking it. We differentiate something to, excuse me, take a derivative. And I can see why, I understand why someone would ask that question, because a lot of people do inappropriately say that they're deriving something when they're trying to find a derivative. I know they sound very similar, but unfortunately, the meaning is not the same. So when taking a derivative, definitely say that you were differentiating something. And then what else? What is the primary reason why this course fluctuates between a variety of different mutation conventions? The professor is lazy is a possibility, although it's not what I think the correct answer is. The class would be too easy otherwise. Also don't think that's true. This is meant to prepare you to apply calculus in a variety of different contexts. I mean, I'll be frank, I also use different notations, right? I fluctuate back and forth between dy dx or d dx of whatever your function is, or writing f prime of x. It's really because everybody uses all these notations all the time. So it is meant to prepare you to see the things. And also, I guess, yeah, I mean, sometimes we say like we're going to find y prime, but then it makes sense to write the function as f of x because it makes it easy to say something about it. So sometimes we change here in the problem. Find a function f prime of x. I like this last question. I'm right, throwing things in the wrong place here. Find a function. I'll just move this over here. Find a function f of x such that f prime of x equals f of x for all x. We know a function like that. We know that f prime of x equals f of x if f of x is equal to e to the x. Okay. But you could also multiply this by any constant if you want. So it's really more generally true if f of x equals any constant you like and d of x. So what I want to do now is then say if I want f of 1, well, if I plug in 1, it's going to be the constant times e to the 1, and I want that to equal 1. And if I solve for this constant, that constant is equal to 1 divided by e to the 1. So really the function I'm looking for is f of x equal to 1 over e times e to the x. Or if you want to be fancy, you could write this as, well, that's e to the x over e to the 1. And then e to the x divided by e to the 1 can subtract those powers and say it's e to the x minus 1. Check it out. F of x equals e to the x minus 1. Both things work. F of 1 is e to the 1 minus 1, which is e to the 0, which is 1. And f prime of 1, sorry, f prime of x, derivative e to the stuff is e to the stuff times the derivative of the stuff, but the derivative of x minus 1 is just 1. So here's a function, e to the x minus 1, or 1 over e times e to the x, the same, whose derivative is itself, and if you plug in 1, you get 1. All right, that's all I've got time for today. You should all check if you're seeing this part, you've watched the video, so it seems silly to say you should all watch this video. But you should all watch this video before class on Tuesday, and I'm not sure what we're going to do on Tuesday. We'll probably have more about derivatives on Tuesday. Also, I am going to post a derivative worksheet that I think I might have already posted it, but either way, I'll make sure that on Canvas in the modules there is a derivative worksheet along with solutions. It is like 30-ish problems, but there's a lot of good practice in using the product rule, the quotient rule, and the chain rule. So I would, if you're looking for more practice about differentiation, not derivation, differentiation, I would encourage you to inspect that because I think it's worth it. In fact, let's go ahead before I sign off here. Let's go ahead and take a look at Canvas and just see here. 1 second. Let's check out Canvas for a moment. Sorry, I'm not showing you. Let me show the screen. This. Let's see. Canvas. Scroll down, scroll in, that's recordings. This is down. I guess that's all there is. So I guess I don't have those handouts. That is surprising. That's not even good. Great. Well, I will post that handout that I'm referring to. I'll probably post it. Either it'll be in the modules, either here or down here. And yeah, I hope you all do well on the test on Monday or Wednesday. I don't know what day it is. If I don't see you before your test, I hope it goes well. If I do see you before your test, I'll wish you well. All right. Take it easy. Have a nice weekend. Watch this video.